Okay, so let me start by talking about NetInt for a bit. NetInt sells ASIC-based transcoders. We've shipped transcoders based on ASIC since about 2019. And as far as I know, we're certainly the only vendor who's been shipping ASIC-based transcoders since then. And I think we're still the only third-party vendor who sells ASIC-based transcoders. There's some companies coming into the market, but I'm not sure they're here yet. And we'll see why that's significant in a moment. So here's our agenda. I want to talk about our transcoding options for large scale events. We'll cover the type of event that we're discussing in a moment. And then I want to talk about the criteria used to differentiate between the various transcoding alternatives that you have. And one of those is what I call the operating point, which is basically understanding the parameters that you're going to use when you're actually producing. And we know that involves things like presets that trade off quality versus throughput. So understanding the parameters for each product that you're working with to make sure that you're using the configuration that you want to use for production, and then running your quality and throughput comparisons. And I call that the operating point, the actual production configuration you use. And then we're going to look at three product comparisons. One I produced, and that compares CPU-based transcoding in terms of quality and throughput with the NVIDIA T4, which is a GPU-based transcoder, and the NetInt Quadra product. And then we'll look at two other transcoding studies, one performed by our director of customer service or field application engineering, and he compared the L4, which is a more advanced NVIDIA GPU, and then one produced by a customer of ours where he compared CPU transcoding, NVIDIA T4 transcoding with our Quadra. And all these studies looked at both quality and the cost associated with the different transcoding technologies, including capital cost and operating cost. So the focus of our products typically is high density live streaming. So it's cloud gaming, gambling, interactive videos, AR, VR, and metaverse. And I'm not going to talk about VOD or encoding for single user origination. So if you're looking for, if you're using Wirecast or you're producing a stream that you're sending out to the cloud, say a service like Movie for transcoding, we're not covering that origination. We're covering pretty much the transcoding space, and it sounds like Movie would be a great customer for our products. The first point I want to make is that if you're looking at high volume transcoding, software encoding or CPU-based transcoding with FFmpeg is simply ineffective. And let me show you what I mean. This is a comparison of three computers with two different configurations. One, the T408, which is an older version of, or the first version of the NetInt ASIC-based transcoder, and then X.264 using the fast preset. And these are the results for H.264 output with the T408, and this is the software-only output. And we're comparing frames per second, watts consumed, and frames per second per watt. So what we see is that we've got 10 ASIC-based transcoders in a single server, and that server is producing 4164 frames per second and only consuming 369 watts. And that's because one of the benefits of ASICs is that they're very power efficient. On the other hand, we see each of these computers producing much less output, but they're producing about the same power consumption because the CPU is the most power consuming device in a computer, and it's running at full bore to produce the software output here. So the power consumption is about the same, which means the watts per stream are about the same, but the frame per second output to H.264 is 13 times higher with the ASIC-based transcoders than with CPU. And that means if you want to produce the equivalent number of streams with software only or CPU-based encoding, you're going to have 13 machines running, and that's going to be 13 times the power, 13 times the capital cost. And then with HEVC, it gets even worse because HEVC is a more complex codec. The thing to understand about most hardware-based transcoders is that with HEVC, or AV1 for that matter, you don't slow down the transcoding the way you do with software because it's all done in hardware. So the throughput is pretty much the equivalent for all of the ASIC-based transcoders, whether it's H.264, HEVC, or with the Quadra, which also encodes to AV1. So throughput doesn't slow down just because you're using HEVC with hardware. But if you're doing that on the CPU, it slows down considerably. So we have the same 3 machines. And again, we're running HEVC output with the T408 over here, and then software only output using the X.264 medium preset in this case. And we see again that power consumption is about the same. We're not increasing the power consumption of the T4s because we're encoding with HEVC. It's done in hardware, so it's all very efficient. On the other hand, the software output again is going to be full bore on the computer. But what we're seeing is where X.265 produces 74 frames per second, the ASIC-based transcoders are producing over 4,000. So the output is actually 55% or 55 times greater than what you get in a single computer. And that's the power of ASICs. And the bottom line is that software only is just too expensive from both a CapEx and a OpEx perspective for live streaming operations. And it's also, environmentally irresponsible because, in the case of HEVC, you're burning 55 times the carbon emissions to output the same number of streams as you do with ASIC-based transcoding. And we'll look in a moment, this is not just NetInt saying this, we'll look in a moment to see what Google decided to do and what Meta decided to do to handle their transcoding chores. But I think if you're looking at high volume software's kind of out. We'll spend a little bit more time on this, but then we'll focus our the primary analysis on GPU versus ASIC, which is I think the hardware alternatives that most people consider. So the hardware alternatives, I'm being a bit complete here. So I'm going to include CPU, GPU, FPGA or field programmable graphics, not graphics, but should have known that, field programmable something array, and then ASIC. And ASIC stands for application-specific integrated circuit. I've got that one right. And let's compare the alternatives. So the CPU, what is it? It's a simple central processing unit for your entire computer. Incredibly powerful device, runs the entire computer. One example you might consider, and this is obviously on the expensive side, is the Intel Xeon Platinum 8280, which costs $22,500 and consumes 205 watts. So again, when you look at a computer, the CPU draws the most power of any device in the computer. It does all the work, draws the most power. GPU is the graphical processing unit. It drives your graphics. Example is the NVIDIA T4 that I just mentioned a moment ago. The cost of that device is around $2,300 and it draws 70 watts. And gate array. So it's field programmable gate array. And this is a programmable device that can do many things. There's not a lot of products out on the market that use FPGAs because they're generally expensive. But the advantage is you can send programming code into the hardware or the firmware, and then it does a specific task. One example is the AMD Xilinx Alveo U30 that costs around $2,000 and it draws 75 watts as well. And then we have the application-specific integrated circuit. All it does is process video. So, CPU is a general purpose device. GPU is a little bit more focused, but it's still general purpose. It does a lot of graphics work and then it can do AI, it does a lot of other things. What an ASIC does is solely transcoding. And we're talking about the NetInt Quadra, and that costs around $1,500 and it draws only 20 watts. So you see right away that the ASIC is going to be least power consumption of all alternatives. And let's talk about the physical integration and some other aspects of actually implementing these devices in high volume transcoding settings. So CPUs on the motherboard, which really sets a limit on how many CPUs you can put in a single computer, 2, maybe 4, but that's about it. Software integration is typically FFmpeg or an SDK. The percentage of the chip that's devoted to solely transcoding is very, very small. Some Intel CPUs and some AMD CPUs have transcoding only circuits, but it's a small percentage of the overall gate on the entire chip. So if all you're looking for is transcoding, it's a very inefficient way to get it. Encoding throughput is therefore modest. The cost per stream is very high because you've got a very expensive device with only a little bit that's dedicated to transcoding. And then the power usage per stream is very high as well. CPUs are very power consumption, that very little of it is devoted to transcoding, so you're going to have a high power consumption per stream. And this makes it very, very hard to create high dense high density solutions for transcoding with CPUs. You just can't pack that many of them into a single server. And even if you could, the power consumption is going to be very, very excessive, and the heat generation is going to be excessive. So looking at the GPU, this typically is integrated via PCI board. Significance of that is most servers have a limited number of PCI slots that you can use to insert cards. So if you're trying to get, one server that can really transcode hundreds of streams, it's very difficult to do with the GPU. You'll see an example of that later on in the presentation. Again, the percentage of the chip devoted to transcoding operations is relatively small. The GPU does a number of fantastic things. I mean, if you're a gamer, drive your game platforms, if you want to do AI with it, you can do it. There's a bunch of CUDA cores on NVIDIA that can do a lot of different things. But the gates associated with transcoding is a very small percentage of gates on that chip. And that means it's inefficient. It's not going to have great throughput, and it's also going to be high power consumption. In terms of high density installation, creating a server that can encode, again, hundreds of streams, very difficult to do that with the GPU because you just have limited slots available for a GPU that's based on a PCI architecture. FPGA, a lot of the same thing. Typically, that's integrated via PCI. Software integration is going to be the same for all these products, which makes it easy to integrate ASIC-based transcoders, or basically it means that any of these products are going to be pretty easy to integrate into your current encoding stack. Percentage of chip available for transcoding is a bit more than GPU, but not as much as ASIC, which brings down the cost per stream a little bit, as well as the power per stream a little bit. Again, very challenging to do a high density transcoding server based upon FPGAs because they're PCI based and you typically have limited PCI slots in your server. ASIC-based transcoders, the net-in transcoders, one of the unique capabilities of our products is that they come in the U.2 form factor, which is a form factor that's used for high density storage. So it's very easy and very affordable to get a server that's got 10 or even 20 U.2 slots, which means you can put 20 transcoding devices in a single server, which gives you very, very high density. Again, if you're trying to produce a machine that can produce 300 or 600 output streams from a single 1RU slot in a server. Again, you address our products via FFmpeg and an SDK. The percentage of the chip available for transcoding is, as much of the chip as possible. It doesn't do anything other than transcode and supporting operations, which makes the power consumption per stream very, very low. And it also makes the throughput very, very high. And then, this is what I referred to before. What alternative did they choose? If you look at Google, who is in charge of, YouTube or owns YouTube, encodes or transcodes more videos than any platform in the world. And they chose to develop their own ASIC-based chip because that was the most efficient and gave them the highest throughput. Some articles said that it allowed them to not buy over 10 million servers because they developed their own ASIC. Obviously, that's an expensive task beyond most companies, but in Google's case, it makes sense to, not to deploy a GPU, not to deploy an FPGA, but to build their own ASIC. And Meta, Google did this in 2022. Meta announced their chip this year, and they did their own encoding ASIC as well. So the bottom line is that two of the largest video producers in the world built their own ASICs to most economically manage their transcoding load, but neither sells their ASIC. While ASIC has been selling ASIC-based transcoders for over 4 years. So, obviously I think ASICs are best, but when Google and Meta make the same decision, it puts a lot more weight behind what it is that I'm saying. Okay, but you're going to be looking at probably not FPGAs, but you're going to be looking at GPU versus some CPU, maybe if you're not convinced that it doesn't work for you in high volume installations, and you may be considering different ASIC devices when different, when ASICs come from different vendors, which obviously they will over the next few years. So what analysis should you do when choosing between the alternatives? Most important thing is to understand the factors that impact quality and throughput, and we'll cover what those are for the Quadra product. We'll cover what those are for NVIDIA later on in the analysis. And then you should test with a variety of content types, obviously with the content that's important to you. If you're a cartoon channel, you want to test with animations. If you're a sports channel, you want to test with sports footage. And then choose your operating point. Operating point is essentially the configuration you think you'll use during your actual production. And that's going to balance encoding quality and encoding throughput in the case of live streams, which is what we're talking about here. And then do the math. That should give you a quality comparison. That should give you a cost per stream from a CapEx perspective comparison. And it also should give you an OpEx comparison that includes both power consumption, which is the main operating cost, as well as co-location. If you need to locate these in a facility, you'll understand how many servers you need to pay for on a monthly basis, which is going to impact your OpEx costs as well. So let's look at the quality side. And a word about quality. I want to kind of set expectations here and let people understand the quality that ASIC-based transcoders and GPUs, for that matter, are really targeting. And in most live transcoding settings, we saw this a few minutes ago when I was comparing the throughput for X.264 and the T4 or the T408 product from NetEnt. And we saw that I used the very fast preset. And that's because if you're producing live, you need to use a fast preset to get reasonable throughput from your encoding server. So, with X.264, X.265, you typically see different customers using between the medium to ultra fast preset. And then with SVT AV1, which is an AV1 option, then you also see producers using the presets 10 to 12 because that gives them reasonable output throughput, within a server that's encoding CPU only. Now, most hardware encoders can perform within this range, and we'll see examples of that in a moment. You're not going to get, so the thing you get with the software transcoder is you can say, I don't care if this takes all day. I want to encode this to produce the very, very highest quality at the very, very lowest bit rate. And with hardware-based transcoders, you can get quality that's up to a certain level, and we'll see what that level is in a moment. But everything that we do in the Quadra and everything we do in the T408 is live, which means if you don't produce 30 frames per second, it's not usable to the producer who wants to produce an output stream live. So we're not going to equal the tippy top quality that's producible via X.264 or X.265 using the very slow or the placebo preset, but we're going to get within a very relevant range, and we're going to exceed the quality that you can produce with software-based transcoders if you were encoding using a preset that you would use for live streaming, so you could get the throughput, meaning somewhere between medium to ultra fast. And basically the reason for that is that hardware limits the operations that you can do in the hardware should they get to throughput. And we'll see some pretty impressive throughput comparisons in a moment. So this is the classic quality encoding time by preset. And this is for VOD, not for live. And what we're seeing here is that, these are the very familiar X.264 presets from ultra-fast to placebo. This is encoding time on a percentage. So ultra-fast takes 5% of the encoding time of placebo. This is average quality, then blue, and then in red, we see low frame quality. Low frame quality is the VMAF score for the lowest quality frame in the video, and that's an indicator for transient quality problems. So if you use the super fast preset, you get 95.6% of the quality of average quality. So it's not too much below very fast, significantly below faster, but you have a much greater risk of having transient quality problems, 10 or 15 frame quality lapses that your customers will notice and will reduce the quality of experience. So whenever you're doing any kind of comparison, hardware, software, I recommend checking both average quality and low frame quality. And again, low frame is an indicator for transient quality problems. But this shows the overall quality that you can reach with the X.264 preset, obviously with 100% over here, with a much longer encoding times, and down here, lower average quality, much lower low frame quality, but much faster throughput. Now, this is low resource, low quality. This is balanced, and this is very resource intensive. This is the absolute highest quality in the absolute longest encoding time. And mostly, in terms of who uses these presets and for what applications, you see premium content VOD might use slow, slower, and very slow. But most live productions, and this is what I mentioned a moment ago, will use from super fast to medium. So this is the range that you have to target to get good throughput with a CPU-only transcoding setup. And this is the target range that ASICs tend to shoot for. So anywhere between very fast at the low end to slower at the high end. And like the presets you see here, hardware-based transcoders have configuration options that let you trade off quality versus throughput. And we'll see those when we look at the operating point discussion in a moment. So where does Quadra quality fit? And Quadra is the ASIC-based transcoder. It's the newest one from NetInt. Currently the top of the line. It outputs H.264, HEVC, and AV1. And the test overview that we're going to use to compare against the T4 in this case is it involved 5 files. One a sports file, the Tears of Steel animated file, Grand Theft Auto, that's a game file, Meridian, which is the Netflix file, that's kind of a movie-like file, and then Dinner Scene, which is a very low motion test clip from Netflix as well. And then we use different encoding ladders for each to produce VMAF scores between 85 and 95 for the top rung of that ladder. The encoding parameters that I used when I encoded for NVIDIA, I used 2 NVIDIA documents as guides. Links are in the handout, which if you want, contact Movie and I'll make it available to them. And also these video benchmark assumptions, again, a link is in the document. And what I measured was overall VMAF using the harmonic mean, low frame VMAF, as I expressed, it's a measure of the potential for transient quality problems. And this is what it looks like. This is a rate distortion curve for people who haven't seen one of these before. And to create a rate distortion curve, you encode each file 4 different times at 4 different bit rates. So here we see the bit rates ranging from 2250 to 4750. And this is the average of the 5 files that I tested. And then you plot the bit rate and the VMAF quality in this case. So all the files are relatively consistent when it comes to bit rate, which is what you'd want to see. And then once you do the plot, higher is always better. So the technology that ends up on top basically shows the best quality at any bit rate along that curve. Lower is obviously worse, and distance matters. So if you see the kind of distance here between these 3 files, you can basically say, yeah, there's a mathematical difference, but nobody is going to be noticing that. And for reference, most people assume that if you don't have a VMAF difference beyond 3 to 6 VMAF points at the 1080p, high end of the range, nobody's going to be able to see the difference. So if you see a, half a VMAF difference or one point VMAF difference, it's not going to be noticeable by your target viewer. So going through it, here we see the Quadra, which is in red, is slightly higher than medium or NVIDIA. Would a viewer notice the difference here? Probably not. It's always nice being on top, but it's not a big difference here. But we see, Quadra is very far ahead of very fast. So if you're currently encoding with the very fast preset for live presentations, Quadra's quality should be noticeably better than the quality you're getting using the very fast preset. And again, you would use the very fast preset because you need to get reasonable throughput out of your CPU-based transcoding setup. So this is the summary of H.264, and this is low frame. And again, this is an indicator for transient quality problems. We see Quadra, again, is on top. And we see that it's well ahead of very fast. And, the T4 is down here. We're seeing a little bit of, issues or the propensity for issues for low frames that will be much worse with HEVC. We'll see that 2 slides from now. And then we see HEVC. This again is harmonic mean VMAF. Quadra is again on top and medium than NVIDIA. And here we're seeing, a little bit more difference. I'm not, I can't say if this is noticeable, but we're saying that, this is around 86, this is around 89. So you're getting close to that 3+ VMAF difference that people might notice the difference at this quality level. Probably wouldn't notice the difference here, at the 3500 bit rate, but they might notice the quality difference here. And then this is the HEVC low frame that I talked about a moment ago. Quadra gives you the best chance of not having transient quality problems. NVIDIA down here, especially at low bit rate, shows that it might have some issues with low frame. So that would be a concern if I was looking at the NVIDIA T4 GPU. So, hold your thoughts at the conclusion. I want to cover what operating points are and why they're important. But if, as it relates to CPU-based transcoding, if you're using the medium preset or even the slow preset, Quadra's output quality in hardware should equal the quality of what you're getting with X.264 in software, and the throughput should be much, much greater. And then, NVIDIA is a great company. They make great products. I'm not an expert on NVIDIA encoding. I've done analyses like that a few times, so I'm not a complete novice when it comes to it, but, run your own tests and draw your own conclusions. So let's talk about operating point. An operating point is a big deal that's kind of pervade any analysis you do of any kind of transcoder, but in particular hardware, because you really are balancing throughput and quality at the razor's edge. So what do I mean by operating point? Talked about this a few times now. Basically, the parameters that you'll use in a production that you think for your application and your cost structure delivers the optimum blend of quality and throughput. And here's what gets interesting. Vendors produce statistics for throughput. They quote quality results, but you shouldn't assume that they're using the same settings for both. So step one, whenever you're analyzing any transcoder, and it's easier with software than it is with hardware, but you need to identify the critical encoding parameters that impact quality and throughput. And for the Quadra, the two parameters that you may want to adjust are look ahead, which is how many frames the encoder looks ahead before it does the encoding. And obviously that decreases performance and increases latency. If you have a 40 frame look ahead, you've got 40 frames of latency. And also rate distortion optimization, which is basically just another name for a preset. If you just think preset when you see rate distortion optimization, understand that. The higher the preset with Quadra, if you go up to 3, it's the high quality, low throughput. If it's preset 1, it's lower quality, higher throughput. And we'll see examples of how these impact both, really quickly. And then you test in logical configuration. So I basically said, if you're testing Quadra, you want to adjust look ahead and you want to adjust the rate distortion optimization to understand the different quality levels that you can achieve with the device. So what I tested with was rate distortion optimization for H.264. There's only 2 values, 0s and 1s. For HEVC, there's 1, 2, and 3. And then for look ahead, I tested with 40 frame look ahead, 20 frame look ahead, and 0 look ahead. And then I checked the number of streams that I could encode at 30 frames per second in groups of 4. So what I did was it's pretty simple and pretty low tech, but I, loaded up a server, created separate instances for each transcode, and then each group of 4, I would see, okay, are all transcodes above 30 frames per second? Okay, in this configuration, it could do 4. And in this configuration, once I added another one, the frames per second dropped below 30 frames per second, which means I had to back off either instances or change the configuration options. And then I measured the VMAF-related data, which primarily was harmonic mean average score, and then the low frame score that I referred to a few times. So this is the consolidation of all the data that I just talked about. And what I'm doing here is presenting the quality level that I output using X.264. So a lot of times when we talk about transcoding quality for hardware-based transcoders, we relate it to an X.264 level, because everybody knows, okay, X.264 medium is pretty good quality. X.264 very slow is really good quality. X.264 very fast is subpar quality and may have low frame issues. So what I wanted to do was kind of peg the quality of the Quadra for H.264 output to the X.264 presets that you know and love. So what we see is in the highest quality setting, so this is look ahead 40 rate distortion optimization 1 for H.264, the quality that we were able to produce was about the same as slow. And obviously that's going to drop. Here we see that it's look ahead 40, but rate distortion optimization 0. We've decreased the quality by about 1.6 points here, but we've increased the throughput from 16 streams, again, these 30 frame per second streams, to 24 streams. And then if we go to faster, we're down to 92.89, still pretty good quality. Stream count stays about the same. And then if we drop to look ahead 0, rate distortion optimization 0, we're dropping quality by around 4 VMAP points, which is, again, it's not end of the world, but it's probably going to be noticeable by some of your viewers. But we're increasing the throughput from 16 to 36. So when we looked at the operating point that I compared to the NVIDIA T4 in this analysis, this is the configuration that I used. So I didn't test with the fastest configuration. I tested with the highest quality configuration. And this is the decision that you're going to have to make. But the point here is that there's some big differences, right, in terms of quality here and throughput from 16 to 36 and from 94 to 90. I mean, you need to identify the configuration that's best for you. Sometimes it's the best possible quality, sometimes it's the best possible throughput. But until you go through that analysis and identify the configuration that works for you for all the products that you're considering, you really can't compare the products in any kind of reasonable way. So this is what we use for H.264 to compare to the NVIDIA. And same analysis for HEVC. So here's the equivalent points with X.265. And we see, again, that at the highest possible quality setting, lowest throughput, and here for HEVC, we've got look ahead 40, rate distortion optimization 3, LA40 2, LA40 1, and then we drop to 0 for rate distortion, and then drop to 20 for look ahead, and then 0, 0. This is our fastest, lowest quality option. This is our slowest, highest quality option. And we see that the quality here is really good, but the throughput is kind of lagging. And we see the throughput going from 4 to actually 40 streams, which is very impressive. Excuse me. So again, we've got pretty much slow quality with these two configurations, and even this configuration is very close to slow. Then it drops to medium at this throughput point, medium here as well, and then this quality is closest to very fast. And what we used for the comparison in this case was look ahead 40, rate distortion optimization 0, because that gave us medium quality with very, very good throughput. Not the top throughput, not 40, but 28 is still a pretty good result, particularly as compared to what we saw with NVIDIA. And then for NVIDIA, the key configuration options were presets that work like X.264 and X.265, except they're numbers, not names. And we tested preset 1, 2, 4, 6, 9, and then look ahead as well. And we tested 15 and 0 because values higher than 15 crashed the hardware decoding, which would have obviously impacted performance. We used, and when I say hardware decoding, I mean you can decode the incoming H.264 stream on the NVIDIA card, just like you can with the NetInt card. But if you used hardware-based decoding, it crashed with a look ahead over 40. You can also decode in software, which I did, and the quality difference with the look ahead of 40 frames wasn't that substantial. So I only tested it 15 and 0 so I could transcode and get my comparative numbers using hardware-based decoding on the NVIDIA, like I did for the NetInt cards. And here's what I found for NVIDIA. This is the highest quality setting. This is the lowest quality setting. This is the throughput. This is the throughput here. And the quality delta between the presets just wasn't that significant. So this is 93.68. And the same quality was, very similar through all these, dropping to 92.6. So we saw a 4-point difference with Quadra with H.264, and we see a 1-point difference with NVIDIA. And that means there's not going to be too big a difference on the throughput numbers, and that's what we're seeing. What's also interesting is that the throughput and the quality isn't linear. So with Quadra, what you saw was a nice, increasing throughput, for the throughput number, and a reasonable drop in quality for the quality number. And here we're kind of all over the map. We actually get the best throughput at what should be a medium setting. And we get, this what we'd expect, this what we expect. We wouldn't expect this here. And then we wouldn't expect pretty much the highest quality down here. So there's not that much differential. I would find these pretty challenging to use, but the comparison point that I used was, a little bit lower quality, but pretty good throughput here. So this is what I compared to the NetIt numbers. And from a HEVC perspective, kind of the same thing, more nonlinear results. So here we get 3, 3, 16, which is great. But in this configuration, with the same look ahead, but a theoretically lower quality preset, the throughput drops from 16 to 4. And then, so this doesn't make a lot of sense, but this is the operating point that I use for NVIDIA. And then what we do is we compare the two technologies based upon quality and operating point. So these are, this is the operating point for NVIDIA, this is the operating point for the Quadra, and we see that the Quadra delivers 34% less cost per stream, 71% less power per stream. The VMAF average is about 1.6 points higher, on the range of something that might be visible to a target viewer, but certainly below the 3 I quoted before. And the low frame score is 12%, which is certainly something that a viewer would notice, because that's going to translate to, in this case, with those percentages, it's going to translate to a 10 to 12 point VMAF difference, which if that's a transient quality difference for over 10 or 15 frames, that's something a viewer is going to notice. And then same comparison for HEVC and the cost per. Let me go back to the NVIDIA slide. This is where we got the cost per stream. We looked at the cost of the unit all the way at the start of the presentation, and then we divided the cost by the number of streams to get the cost per stream. And then same thing from a watts per stream. Here's the cost per unit. Here's the watts per device. Same thing for the two NetIt analysis. So this is kind of the summary for H.264 we looked at a moment ago, and same type of analysis for HEVC. What we're seeing is that the cost per stream, CapEx, is about 63% lower. The power consumption per stream is 84% lower. The VMAF average is higher, about 1 point. People won't see the difference with 1 point VMAF, but it's always best to be the best. We do see a very significant difference of 20 points in low frame score, which tells me that if you're working with HEVC and NVIDIA, you definitely want to check this yourself and make sure that you don't see transient quality issues in the streams. So that was my analysis. This is analysis I put together beginning of this year. We have a second hardware comparison that compares the AMD EPYC 32-core CPU with the NVIDIA L4, which is a newer model of GPU from NVIDIA, and then the Quadra T1U, which is one of our Quadra family. And the codecs we looked at were H.264, HEVC, single file comparison. Typically you want to encode multiple files, but the Meridian clip that's used by Netflix has a lot of different scenes in it that really does simulate a lot of different types of production. So it's a 12-minute video, and I think the results are certainly relevant if you're outputting entertainment type content. We looked at the average quality, we looked at low frame score, we looked at performance. So here's the H.264 quality in a rate distortion curve output format. We see the Quadra, in this case in red, is again tops. NVIDIA is second in gray. Very fast is all the way down here, and medium and black is down here. So Probably not a huge difference in terms of anything viewer would notice, but again, it's always nice to be on top. Low frame score here. We actually dropped below NVIDIA in this case, but again, the delta is less than 1%, so it's unlikely anybody would notice the difference. For HEVC, what we see is Quadra is again below NVIDIA, but the delta is 0.04%, not something any would notice. But if you look at the low frame scores, NVIDIA again drops into a concerning deficit here, which means that if you're looking for HEVC transcoding with NVIDIA, either the L4 or the T4, you've got to really consider low frame quality because it may be an issue. On the performance side, we see pretty much what we saw a few moments ago. We looked at capacity, power consumption. We calculated costs, assuming 320 channels to supply, and we looked at cost and power analysis there. And for these tests, all output streams are 1080p 30. So what we saw for server capacity, this is an individual server, the CPU could produce 15 output streams at 1080p 30. The NVIDIA L4, you'd had to add 2 add-in cards that would increase the price of the machine to around $14,000. The capacity was around 50 streams, which produced a cost per stream of $285. And the Quadra video server has 10 T1Us, and the capacity for that device was 320, which gives you a cost per stream of around $65. So software only, GPU, CPU. In terms of power consumption, these are actual numbers measured, and we see, this is the total output side. Really don't need to know this here. Capacity is the same, and this is the watts per stream. So we're seeing, as we talked about at the very start, because most of the ASIC is devoted to transcoding, it's a very efficient transcode from both a throughput and a power consumption perspective. Now, if you're producing 320 channels, what do these numbers look like? With the CPU, you have to buy 21 servers, which gives you a total cost of around $151. With the NVIDIA L4, you need 6 servers, which is $90,000. With the Quadra video server, 1 server can produce 320 output streams, which gives you a total cost of $21,000. And then these are the equivalent numbers for power consumptions. So total wattage will be 8,200 for CPU, 3,480 for the L4, and 450 for the Quadra video server. And this, this is for H.264 only. So this shows, on the power side, the Quadra-based solution uses 95% less than CPU only and 88% less than the NVIDIA. And then on the server CapEx cost, we're 86% lower than CPU only and 77% lower than GPU. Looking at the HEVC side, similar types of numbers. The cost per stream for CPU is going to be much higher. Back at the start, we looked at 55x more efficiency for hardware than software. So here we're seeing you need a ton of servers. You need 46 servers to produce the same output as 1 server with 10 ASICs in it. So server capacity, the CPU can produce 7 streams. Cost per stream is $1,000. NVIDIA L4, total cost of the system gives you a capacity of 40 for around 355 cost per stream. And then the Quadra video server is very similar. As I said, the capacity really doesn't change whether it's H.264, HEVC, or AV1 because it's programmed in hardware. It's not done in software. So throughput should be very, very close to the same, but probably not identical. That's server capacity. This is power consumption, same watts per stream for the Quadra video server. Increased watts per stream for CPU, or about the same on a watts per stream basis. In terms of total watts, it's going to be much higher. And this is that analysis. This is the total server cost. We need 46 servers for CPU only to produce the 320 streams that we're working towards. That's a total cost of $324,000. NVIDIA, we need 8 servers at $14,000 each, which is $113,000. And the Quadra video server, we can do this in 1 server, which costs $21,000. In terms of power consumption, it's 18,000 watts to produce these 320 streams. Obviously, that's very ecologically unsound. NVIDIA is quite a bit lower, but still over 10x higher than what you get with the Quadra video server. So these are the numbers. HEVC is in gray, H.264 is white, and this is power savings. As compared to CPU only, the HEVC saving is 98%. And in terms of CapEx, it's 94% savings. And then you see for H.264, the power is 88% less within the NVIDIA solution, 90% less than for HEVC. And for capital, it costs you 82% less to implement transcoding in Quadra than in the GPU-based solution for HEVC, and 77% less for H.264. And then here are the command strings that we used. And again, if you want a copy of the handout to look at these in detail, you're welcome to request it from Movie, and I'll make a copy available to them. Now, so the first two analyses were done by one by me and one by our field application engineering head. So they're both by NetInt. You could kind of say, okay, are they objective? And hopefully, I've tried to be objective. These, I've published a lot of technology comparisons in my day, a lot for streaming media, or most for streaming media, and I use the same procedures that I did for them for the analyses that I did for NetInt. All that said, this analysis was produced by an actual customer who was evaluating multiple alternatives to achieving a very high-end result, and ultimately came down and concluded that ASICs were the most efficient. So their particular requirements were 10,000 incoming streams 24/7, it's a worldwide operation, 1 million outbound streams, and very, very low latency, as low as possible. So this is a very large volume operation. And they had one input stream coming in via WebRTC, and they had a 5-rung encoding ladder going out. So this is what they were doing on the transcoding side. And they tried a CPU-based transcoder. Now remember, they had to achieve they had to handle 10,000 incoming streams and output 1 million output streams. So here we see the transcoders X.264 in software. They could get 20 output streams from a single, I guess this is a 3RU server, and power consumption was 650 watts. The server cost them $20,000, so it was $1,000 per stream. To meet their 10,000 stream input requirement, they had to buy 500 servers, which is very, very expensive. In this case, it would have cost them $10 million to do that. Total power would have been 325,000 watts, and annual colo costs for a 3RU rack at $125 per month would have been $750,000. They tried the NVIDIA T4 GPU. That dropped the number of servers down to 105 and dropped the stream cost from 1,000 down to 333. Total CapEx went from 10 million to 3.4 million, which is quite substantial, and total power dropped significantly as well, as did the average. And we'll look at summary numbers of this in a moment. Now, the Quadra T2, which is a different card than the Quadra that we looked at in the first couple of test cases, they were able to drop the required servers from 500 with software only to 38 with Quadra, and from 105 for the T4 to 38 for Quadra, which dropped their CapEx from 10 to 3.4 to 1.4 million, and dropped their power consumption and their annual co-location costs quite significantly as well. And this is what the numbers look like from a total operational comparison. So here's the CapEx, CPU software only, 10 million, NVIDIA T4, 3.36, Quadra T2, 1.44. Per stream cost we see here, annual co-location. This, do the math. This is just based on the number of servers that you had to support. And this is total power production in watts, which drops nearly, 90% from software only to 112 for NVIDIA, to 34 for the Quadra T2 based solution. And the quality checks they did, they wanted to make sure that the quality was going to be the same for the 3 different approaches. So first to come up with their optimal parameters for each encoder, they checked with PSNR and VMAF. Then they did subjective testing by business representatives. And then finally, they did user surveys among their viewers to make sure that the quality of all three alternatives was about the same. And again, they were a low latency solution. So these are, this is a summary of the encoding settings that they used. So they used a faster preset. Again, use a faster preset to get even reasonable throughput. But it was zero latency and no scene cut, CBR, and no B frames because it was a live low latency configuration. And okay. So the conclusions, we started this right at the top. CPU only is expensive and it's environmentally unfriendly. If you're doing large scale transcoding with CPU, if you've already got the equipment, it's hard to throw it away, but you're going to be spending a lot more on power cost than you would with either GPU or ASIC-based transcoding technology. ASICs were preferred by Google and Meta. I think, if you had the option to use an ASIC, it's always going to be the most affordable from both the CapEx and an operating cost perspective. If you do decide to compare hardware alternatives, and this is either, GPU versus ASIC or ASIC versus ASIC, you need to understand the key configuration options for each encoder. You need to identify the relevant operating points for the two encoders so you're comparing apples versus apples and you understand the throughput and quality at those relevant operating points. And then you compare the quality. I use VMAF, but I look at both average and low frame. Low frame is a measure of the transient issues. And then, one of the nice things that Mayflower did is they introduced subjective comparisons into the picture. Subjectives are the best. They're hard to do, expensive, but if you've got millions of customers out there, it's pretty easy to throw a survey at them and just get their conclusions as to which quality they think is best. Once you understand that the quality is more or less equivalent, then you want to compare the cost per stream and the total CapEx, the watts per stream and density. And I keep bringing up density because the number of servers determines what your co-location cost is going to be, or your internal expense for housing those servers, plus the maintenance cost, which we haven't even covered. It costs a lot more to maintain 100 servers than it does cost to maintain one server. And that's it. That's my talk.
Thank you, Jan. Thank you for this amazing and insightful presentation. Now the questions or Q&As are coming up. I have a question from Andreas, and he wants to know what about more broadcast type of outputs that need pass-through of SCT35 subs, etc. is supported? Quality-based live encoding like capped CRF quality factor or similar, is that possible with NetInt?
Okay, so the SCT35, that's something we've been working on. I don't know the exact, I think we have a solution that's proposed and under development, but I'm not sure it's available yet. Andreas, if you want to contact me, I can give you the answer to that. And yeah, I mean, Cap CRF is a feature that NetInt added to their Quadra and T408 in mid 2033. I've written about it substantially. If you Google NetInt capped CRF and my name, you should be able to find the articles on the website that talks about that. If you can't find them that easily, just email me and I will. I'll send you the URLs.
Well, I hope this answers your question, Andreas. So that's it for today, everyone. This concludes our session. And on behalf of Movie, I would like to thank you, Jan, for agreeing to do this webinar for our audiences. And I'm sure our audiences learned a lot from it. So thank you again for joining this webinar with us.
My pleasure. Thank you for having me.
This concludes our session for today, and to all our audiences, Movie keeps conducting such sessions each month. And for information about our latest webinars on industrial event topics, you can visit our website and follow us on our social media channels and get info about the same. As a token of appreciation, we would also like to give you an informative brochure to read later on live transcoding. And if you would like to know more about how you can set up Movie Live for your live streaming needs, feel free to contact our sales team, which is also downloadable. Thank you everyone for the information of it is also downloadable. Thank you everyone for attending this webinar. I hope you have a good day. Thank you.